All right, this is Earth 101. We're going to be covering Chapter 7 in our book. And Chapter 7 is about the other terrestrial worlds. So the other terrestrial worlds, we know there are 4 of them. Earth is one of them, of course, but the other 3 tonight. The other 3 tonight. So we are living in a pretty amazing time. This is a chance, right at this moment in time, we have spacecraft that are on Mars and orbiting Mars. We have spacecraft orbiting Jupiter. We have spacecraft out beyond Pluto, actually in the Kuiper Belt. We have spacecraft going to asteroids, OSIRIS-REx, and returning to Earth with samples from the asteroids. OSIRIS-REx is on its way. The JAXA mission, Japanese mission. We have all kinds of amazing missions going on. So this is a time of a very, very exciting time where we're learning lots about our solar system. And at the same time, in the last 10 years, we've managed to see other solar systems, other worlds. So what we're talking about tonight are some of the ideas related to terrestrial bodies. And again, these are the ones that we know, the ones that are in our solar system, but we hope that what we're learning about our solar system will be applicable to other solar systems. So this is the Mars Curiosity rover. You need to know that name, Curiosity, and it is on Mars right now and exploring, and it single-handedly has actually been one of the most amazing tools for discovering the course of water. About 3 billion years ago, there was liquid water on the surface of Mars. We'll talk more about the timeline later. And you'll need to understand actually specifically, why doesn't Mars have water anymore? But there's lots and lots of evidence. We have, just all kinds of evidence now. And what's really exciting, I'll tell you about some news that we got about 1.5 years ago from NASA, that there's liquid water under the surface today, right now. Okay, so that's pretty exciting stuff. So it certainly seems as though Mars used to be wet, and perhaps it was as wet as Earth. It had lakes and rivers and clouds and all kinds of stuff. It still has clouds, it still has ice caps, but most of the water on Mars is underground. So it's not on the surface anymore. And why not? What is the reason? The main reason that you can't have water at the surface? Because the atmosphere is not dense enough, right? There's not enough pressure to allow liquid water to exist. So the topic of the terrestrial planets is actually going to go under the heading of comparative planetology. And we're asking the question, how are these other planets in our solar system similar to Earth and then also different than Earth? And could it be that there was life on Mars at one point? Is that possible? And are there other places in our solar system right now where the conditions are right for life to exist? As far as we know, life requires water. So a place that has liquid water, a place that has liquid water would perhaps be hospitable for life. So what other places are there besides the Earth? So we're going to learn there are these stages of the development of a terrestrial planet, and all of them have taken place on the Earth as well as on other bodies in the solar system. And the first one is the formation of the planet. So a protoplanet forms, it's large enough to start sweeping up the area of its orbital path, and then it becomes a full planet, right? Now, the concept of energy is involved here, right? If you take material that's spread apart and you collapse it down to a smaller size, then the gravitational potential energy is converted into kinetic energy, which is converted into heat energy. So any object like a planet that forms from all of this debris concentrating is going to be hot. And because it's hot, it's probably going to be molten. So if a body is molten, what happens as a result of that? It will develop layers of different density. The most dense will be in the center, and the least dense will be on the surface. So this is the process called differentiation. All right, so we've got differentiation, and then what? Well, then some of the heat energy will escape from the body by radiation, and the surface will cool just a little bit, and it will form a crust. So the second stage is called cooling. But we want to understand that at the process of cooling, you form a crust on the surface of your terrestrial body. So cooling, right, that first crust forms and we have a solid surface. Now, we have observed that in our solar system, there was a period after the crust originally formed that the inner solar system was bombarded. We call it the late heavy bombardment, and it's about 4 billion years ago, between 4.1 and 3.8 billion years ago, if you remember. And so the evidence on the moon, because the moon has not really weathered, right? There's no atmosphere on the moon. We believe that that's a really good indicator of the long-term history of our inner solar system. So now, if the cratering events are particularly energetic, what will happen is the crust will crack open and magma from inside will flow out, and you get what is called magma flooding. Okay, so magma, the hot silicate material, flows out of the interior and floods the valleys on the surface of the new body, like the moon, right? And the mare or the maria on the moon would have formed exactly in that way. And it must have happened on Earth as well. Finally, if you have an atmosphere, because you need an atmosphere, the weathering will take place and will modify the surface by wearing down the mountains, right? Even the tallest mountain eventually will wear down because of weathering. So wind, erosion, rain, right? Wind, rain, erosion. So if you take a look, here's a quick snapshot, and I want you to look at them and say, what's the same, right? You'll notice that they all have similar colors, right? So do they have a core? All of them have a core. Do they have a mantle? All of them have a mantle. Do they have a crust? They all have a crust. Are they the same, right? And the first thing that I want you to notice is, what do you notice about the proportion of the total size that is the core? And you might notice that Mercury is lots and lots of core and not so much silicate. Why would that be? And if you remember our discussion, we said that the grains of metal and metal oxide form closest to the sun and then for the rest of the solar system. But silicates, you have to go out a little further. So it kind of makes sense that there wasn't as much silicate material available for Mercury, and that's why it formed with less silicates. That would be an explanation that I could give you. How about the crusts? Are they the same? And the answer is they're not going to be the same either, right? So just looking at the picture, it's kind of hard to tell. The crust is so small in comparison to the size of the planet. All of these are exaggerations. None of them have very thick crust, right? So we'll come back to the actual sizes. But let's take a look at Mercury. So Mercury is just 1.4 times the size of the moon. And if you remember, the moon is 1/4 the size of the Earth. So if you say, 4,000 miles is the radius of the Earth, then you would get 1,000 miles for the radius of the moon, or you would get 1,600 kilometers as the radius of the moon. And that means the diameter is 2,000 miles of the moon, right? And then what would it be for Mercury? Well, 2,800, right? 2,800 miles. So, it's about 3,000 miles across, something like that. And that's less than 2,000 kilometers, right? So you don't have to know the exact number. But anyways, it's smaller than our moon. It's very close to the sun. But would you believe that there's probably ice in parts of Mercury, which is kind of amazing? There are craters on Mercury that are almost always in the dark. And in those darkest craters, it's going to be really cold. So facing the sun is hot, and the side facing away from the sun is very cold, right? It's not receiving the sunlight. So anyways, Mercury does not show any real activity right now. And I actually would have said to you a few years ago that Mercury is pretty much dead. Okay, 10 years ago, I would have said Mercury is dead. But actually something kind of interesting happened, and I'm going to relate to you what happened. NASA noticed something very interesting. Okay, so Mercury has a very weak metallic field, and even though it has a large metallic core. Now, wait a second. We said that magnetic field comes from a dynamo effect inside of the core, right? Like in the Earth. So, but if you were paying attention, you realize that it's not all of the iron core that produces the dynamo effect. In the Earth, what part of the core is producing the dynamo effect? And I can't hear you through the YouTube, but I hope some of you are saying The outer molten core. Okay, that's the requirement. It has to be molten iron. So what would be a good reason why Mercury doesn't have a magnetic field, or very weak magnetic field right now? And again, I'm listening and I can't hear you, but I'm going to hope that some of you said because it doesn't have a molten core. Mercury's core is basically solid now. Why is it solid? Well, because Mercury is so small, when it radiated heat energy, it cooled off very quickly. So a small body like Mercury or the moon would have cooled off very quickly, right? The size of the body, the radius of the body determines how long it takes to cool off, right? So the larger the body, the longer it's going to take to cool off. Why? Well, because it has more heat energy to start with, but also the rate at which it's escaping is going to be less compared to its total amount of heat energy. So the larger the body is, the slower it is for cooling off, the longer it takes to cool off. So here's a really important point. I want to make sure the author kind of sometimes doesn't make it so clear, but please be very clear, Mercury does not have an atmosphere. But wait a second, in the same sentence, we're going to say, but it does have a thin layer of hydrogen and helium. Wait a second, is there an atmosphere or not? And it's kind of important that you know where this hydrogen and helium came from, and also that it is temporary. Okay, so the hydrogen and helium that we see near the surface of Mercury is just temporarily there, and it's going to be blown away, and it's not going to stay. Okay, where did it come from? Well, you might remember that the composition of the solar wind is made of protons, and which are the hydrogen nuclei, and alpha particles, which are the helium nuclei, and electrons. And so I'm going to say to you that the hydrogen and helium came from the solar wind. It got trapped temporarily by Mercury, but it's going to be blown away very shortly. It won't last. Okay, so it's doesn't really count as an atmosphere. It's just temporarily there. It's going to be gone very soon. Okay, doesn't have a lot of gravity, right? It's a small body. So it's going to be a much harder to hold on to the molecules of hydrogen and helium, or anything else for that matter. So when you look at Mercury, there's actually a lot of really cool work that's been done. We see mountains and craters, lots and lots of craters. So what does it mean? Is the surface old or young? And I hope that you're getting the idea that when you see lots of craters, that's an old surface. Some of the surfaces we're going to talk about tonight don't have any craters. And immediately, if you don't see craters, but you know that it got bombarded in the past, you know that that surface is young. So this is a giant impact crater called Coronae Basin. And actually there's yellow, this real yellow color here is from sulfur that was probably came out as a result of some geothermal action. So after the impact, the heat energy caused these vents to vent material from the inside of Mercury, and that residue got deposited on the surface. These are sulfur-containing compounds. Now, I'm not showing you a picture, but on the backside of Mercury, we think that the same event created a set of mountains on the far side. So this vibration shook Mercury so much that it actually formed a set of mountains as it did. We also see some pretty tall mountains on Mercury. When I say pretty tall, actually 8 miles tall, pretty big, right? But they're not active, right? They're not changing. They're pretty much static. So I would have said to you, again, like I said, 10 years ago, Mercury is dead. But I'm going to tell you something tonight that you want to be aware of, that Mercury seems to still have a little tiny bit of life in it. Okay, and I'll talk about that in just a minute. Okay, now Mercury does have a very strange rotation and revolution. It's not tidally locked, but it's on the way to becoming tidal locked. It has a revolution, rotation, resonance, it's called. The rotation, revolution, resonance. And so it takes about 88 days for Mercury to make one orbit around the sun. That's the Mercury year, 88 days, about 3 months. But the rotation period is about 59 days. Now, those numbers are not exact. So those of you good at mental math, let me try this, right? What happens if you multiply 88 times 2 and you get 2 times 88, 176? And what if you multiply 59 times 3 and you get 177? Okay, well, it turns out that if you got the real numbers, you would find out that they equal each other. 2 times the period it takes for 1 year is 3 times the rotational period. So it's not tidally locked, but it's kind of on its way there. And so the tidal forces from the sun are trying to lock Mercury. They haven't quite gotten it there, but it has this very curious orbit, rotation, revolution, resonance. Okay, so rotation 59 days and revolution 88 days. And there's a very funny thing. The day on Mercury is actually pretty strange. Phil talks about that in the video. So how many Earth days is one solar day on Mercury? So, hey, why not? Let's click it. Let's just click it. Why not? All right, so I need to switch to the this new thing so I can see that. And according to this, here's what it says. Oh, how do you calculate? I'm not sure where I did that. Okay, never mind. Skip that. I'm not sure where I have that there. We'll go back to this. How many Earth days is one solar day on Mercury? It's a little funny. Yeah, this is actually, I thought this was a link to a video, but I don't see that. Okay, skipping right along. Here is a Sharpie puppy. Oh, so cute. And you might be like, why are you showing us a Sharpie puppy? This is not puppy class. But when you look at this puppy, the thing that I want you to look at is actually something kind of important, right? There's too much skin, okay? So I think this is a great analogy for Mercury and what I'm about to share with you. So what happens with a Sharpie puppy is they have just way too much skin for their little bodies, and they're so cute. But what about Mercury? Well, it turns out that in 2008, and you should know this because it's on your test, right? NASA noticed that a new cliff had formed. Actually, if you heard Phil, they're called rupas or rupae. And this one is about, I think it's about 6 miles tall. And it's another name, the technical name is lobate scarp. But another non-technical name is wrinkle ridge. And the idea is that the crust of Mercury formed pretty early on. But Mercury has continued to cool and is still cooling apparently, because what happens to the skin when the core cools? Well, it has to collapse and it doesn't have enough room. And so it has to fold, right? And these folds produce cliffs that are called lobate scarps, okay? So basically this new cliff on Mercury means that it's still cooling off, even after all this billions of years. Okay, it's not much, but it's just a little bit of life left in it. And you're supposed to know that, a little bit of life. Okay, so let's go ahead and skip forward to our twin planet, Venus. Venus is, in terms of size, is pretty close to the size of the Earth, but it's slightly less mass, a little bit less density. It has some really interesting properties that you want to be aware of. First of all, we have never seen with visible light, we have never seen the surface of Venus. And the reason is it is always covered with clouds. So Venus is an example of a runaway greenhouse effect. And Phil goes into a little more detail than you actually need to know, but you should know that once upon a time, Venus did have water on its surface, but it lost all of that water because of the extreme heating. So the surface temperature of Venus is 730 Kelvin. That's actually over twice the temperature of Earth, and it's hot enough to melt lead, it turns out. It always has clouds covering it. It does not have a strong magnetic field. That's kind of important. With Mercury, the reason it didn't have a magnetic field was because the core was solid. But we'll find out it's a different story with Venus. But again, you need to understand, why doesn't Venus have a magnetic field? And how have we seen anything anyways? If we can't see through the clouds, how do we see anything on Venus? Well, I'm glad you asked. But before we do that, first of all, Venus, we think, has an incredibly slow rotation period. One rotation of Venus takes 224 days, okay? And the year of Venus is about 256 days. So it actually takes nearly as long for one rotation. Except something important, Venus appears to be rotating in the wrong direction. So you want to write down that Venus has a retrograde rotation, or alternatively, it got flipped over. So actually, I forgot to mention it. How many moons does Mercury have? None. How many moons does Venus have? None. But maybe it had a big moon at one point, right? I didn't tell you that, but maybe. And that whole flipped over thing, maybe something happened, right? We don't know for sure. But when you ask the question, why does something have a tilt? The answer is from collisions from the outside. Okay, it's got to be. If it didn't have any collisions from the outside, then it would not have any tilt. It would be straight up and down. Okay. When I tell you this exciting news, it turns out the Russian government was able to send the Soviet government was able to send a series of missions to the surface of Venus and actually take pictures. And this is an actual picture of the surface of Venus. It's very dry and cracked, and the spacecraft would only last for a couple of hours before it just died. Okay, but it was able to see and actually take pictures. And so you want to know that in addition to the heat, this is a really inhospitable place. The pressure is 90 times the atmospheric pressure on Earth. So not only would the temperature kill us, the pressure would crush us, right? It's just way too much. So we think that the crust on Venus is incredibly thin. And so it could have thousands of little plates, but not really any plate tectonics to speak of. And so the reason is, and on Earth, the plates are big, right? And these plates are able to maneuver and create new mountains. We don't see anything like that on Venus, not really. The only thing we kind of see is these not really volcanoes. They're called Coronae. They're in your book. And they look like these pancakes. Actually, I should have a picture. I don't really have a good picture. Okay. You know what? At this moment, I realized I should have had a picture. I apologize. Let me go ahead and get you a picture so you can see for yourself what a coronae looks like. So they look like pancakes. Okay. And here we go, Wikipedia. We like Wikipedia. So let's go ahead and take a look at Wikipedia. Here's Wikipedia, and this is a coronae. Okay, so it looks like a pancake. Actually, there's a few of them. There's a good one. That's a good one right there. So these coronae, they look like pancakes, but they're actually depressions. So they look kind of like craters, right? Which one are they? Are they craters or are they? What are they, right? And it turns out that they are very interesting things. Actually, you know what? Even with all of this, I'm showing you pictures of coronae, and now I feel like I need to describe it for you a little bit. So let's go ahead and switch cameras, and I'm going to draw you a picture like I would do in the classroom. And let's talk about this. Okay, so a single one is called the corona, right? But coronae, right? They are depressions, and they're circular, but they are really associated with volcanic activity. Okay, so these circles, right, are basically because Venus is so flat, we think that magma came out of the central piece right here and then just flowed in every direction. And these are about, 30 kilometers, 20 miles across, something like that. They're not really big, but again, it was so flat that they flowed in every direction and made circles as a result of that. So how do they work? Well, here's the idea. So this thin surface of Venus is going to be very easy to flex. And so what we have is this upwelling. An upwelling is a push of magma from below, upwelling of magma. So that pushes up. Well, what does it do? It creates this kind of a dome right here. Actually, I don't want to be gross, but it's like a pimple almost. And then it begins to leak, and it leaks out in all directions, and it's going to form this corona, right? And then what happens is that after the upwelling and after the fracture here, and it's not a very energetic thing, it doesn't spew in all direction. It's a very gentle kind of flowing action. But after the pressure recedes, the upwelling recedes, right? And then instead of being a little mountain shape, it's going to actually be a depression, right? Left behind where that used to be. Okay, so in the middle of this thing is actually a kind of crater looking thing, but it's not a crater. In fact, there are no craters on Venus. Not really. And so what does this mean? Is the surface old or young? And you want to know that this is young surface. Some people think that it's less than 1 million years old, right? It's very young. And we don't know exactly how, but we think that maybe once in a while, Venus just kind of resets the surface, resurfaces the entire surface of Venus. Okay, so back to our slide set. And the question is, how do we know that this is what Venus looks like, right? So this is radio, right? So radar is radio. And there's some other really neat things that have been done with Venus, and it has some interesting structures, but there's no big mountains. There's no volcanic activity that we can see at the moment. There's evidence of past volcanic activity. And when I talk about the atmosphere in just a few minutes, you want to know that it has 100% carbon dioxide as a gas in the atmosphere, not like on Earth, which is just 0.04%, right? It is 100% carbon dioxide. So we can look beneath the clouds using radio waves or radar, okay? And so there is no active volcanism on Venus right now, but we may have just missed it. It turns out in the 70s, when they started to look at the gases in the atmosphere of Venus, they detected some sulfur compounds, and those are associated with volcanic activity. But since then, we have not seen any lava flows. But we do know volcanism is a pretty big deal on Venus because the surface is so fresh, right? And the way that you make fresh surface is with volcanoes, right? Whether they're just flowing like the Coronae or erupting. Venus doesn't have so much erupting, so it's mainly this kind of slow flowing, right? Surface has been repaved by lava flows. Okay, so let's talk about that atmosphere. So Venus has 100% carbon dioxide. And we already know that carbon dioxide has a really incredible, powerful potential as a greenhouse gas. Venus has a runaway greenhouse effect. So visible light can enter the atmosphere of Venus, and it is captured, and then it cannot escape. So Venus just keeps gaining energy. So another thing on the previous slide mentioned, because Venus is closer to the sun, the intensity of sunlight is twice as much as it is on Earth. Okay, now here's the good news. Isn't this fun? The clouds on Venus are made from sulfuric acid and other sulfur crystals. Okay, so it actually rains sulfuric acid on Venus. This is not a very hospitable place. So if you were to stand in the rain on Venus, it would not be very fun. But what's very interesting is that it's so hot that the drops of sulfuric acid never make it to the ground. They evaporate and go back up into the cloud layer. So they fall. It does actually rain, but it never makes it even anywhere near the ground. Okay. So people talk about going to visit Venus, but not actually the surface. We do talk about missions. What it would be is maybe way up here above these sulfuric acid clouds, we could have a floating spacecraft that would be, able to keep our astronauts or keep our scientists safe from above the dangerous parts of Venus. So you wouldn't go down into the very thick atmosphere, the high pressure. You wouldn't go into the high temperatures. You wouldn't go into the caustic clouds. You would float above it. But being that much closer, we could do a much better job of probing underneath the clouds. All right, I guess that's it for Venus. Wow, that's it for Venus. Venus, our twin, but not really very hospitable place. Okay, so let's go ahead and move forward to Mars. And actually, you might already know that there's been some pretty good stories, science fiction stories about Mars and the Martians, right? Um, and maybe when you were a kid, you watched Bugs Bunny battling the Martian. But anyways, for years, people considered it a possibility. They saw evidence, they thought, of civilization on Mars. Percival Lowell was actually inspired by an Italian astronomer, and he described these canales, and I'm trying to say it the Italian way. It's not right, I'm sure, but he misinterpreted canales to mean canals, right? That these were like the Venice canals. But in fact, canale just means a culvert, like a gully. And so he misunderstood and made this idea that, you know, there was a whole civilization. And he made maps of these canals that he thought he was seeing. We now know that these are probably just his imagination, but it certainly was intriguing. And H.G. Wells wrote stories about being invaded by the Martians, and some of you may know the War of the Worlds. Right? So Mars right now is cold and dry. Okay, it is small, and so as a result of that, the gravity is weaker. There's a few things that you should know, right? Number one, so the mass is small. I don't think you need to know that it's a tenth, but it's a tenth the mass of Earth. It does not have a strong magnetic field, but it's rotating about the same rate as Earth, right? Actually, its year, how long it takes to go once around the sun, is almost 2 Earth years, but its day is almost the same as an Earth day, right? 24 hours and 37 minutes versus Earth's 24 hours. And interestingly enough, it has a tilt of 25 degrees. So I want to ask you right away, does Mars have seasons? And you would say, of course it does, right? Any planet that has a tilt has to have seasons, right? When the tilt of the planet is toward the sun, it's going to be summer, and in that hemisphere rather, and when it points away from the sun, in that hemisphere is going to be winter. Now, the thing to notice, though, is because the year is twice as long, the seasons should also be twice as long. All right, so you have to know a couple of big features on Mars you want to know. First of all, I see some ice caps. Those are kind of cool. But this big feature in the middle is the largest volcano in our solar system. It is known as Olympus Mons, okay? And it covers an area the size of Arizona. It's taller than Mount Everest, okay? It has a height of 22 kilometers, 13.6 miles, 72,000 feet. Okay, it's twice as big as Mount Everest, right? Actually, is it more than that? Anyways, at least twice as big. So what made it so big? And this is kind of an important thing. We think that the volcano on Mars was similar to a volcano that would be found on Earth. In fact, we give it that name, a shield volcano, like the Hawaiian ones. They build up slowly over time. And so the question is, why do we think that? What is it about the structure that we see? So you want to understand that the volcano works when there's a hot spot, right? There's a hot spot, and the magma can leak up to that hot spot and begin to form this dome, right? And so every time it erupts, it makes a new layer, right? So little by little, these grow. And the Martian one took a long time to grow. So let's see if we can figure out why that would be, right? Number one, does it have a drifting plate? And the answer is, well, you got one big volcano. There were a few small ones nearby, but this is one big volcano. And the answer is the plate doesn't move, okay? So this plate didn't move. In fact, we don't see other evidence of plate tectonic. We don't see plate tectonics on Mars, really, except for this hotspot. So there's no real plate tectonic. In fact, we think that Mars has one plate, right? Because it's cooled off quickly. It's a little more than half the size of the Earth. It built that crust very early on, and then as it cooled off, that crust got even thicker. But that's back to the question, how did you get such a big volcano on Mars? Why don't we have big volcanoes like that on Earth? Well, the answer is we couldn't. It's not possible. If we tried to take that volcano, Olympus Mons, and put it on Earth, it would sink down into the crust. It's too big. It's too massive. So you see, when we analyzed the structure of Olympus Mons, we learned two things. Number one, that the plates don't move, right? They're stuck in one place. And we actually now think that it's just one monoplate, one plate, but also that the crust must be incredibly thick. So Earth has a relatively thin crust. Mars must have an incredibly thick crust to be able to support such a massive volcano. So that's, again, what you want to get, right? Mars has a very thick crust compared to its bulk, and it did not have plates like the Earth. Okay, that's number one, Olympus Mons. Number two is a humongous rift valley. We actually have no idea for sure how this formed. There are lots of ideas. There's lots of, sorry, when I say we don't have any idea, we have no proof of how this formed. We have many ideas. There are several hypotheses. One of them is that there was, Mars has 2 moons. We'll learn about those 2 moons, but maybe it had 3, right? And this is the 3rd moon that is no longer there anymore. There's a reason why I'm telling you that. One of the moons of Mars we know is going to crash into Mars one day. But this valley is called Valle Marineris, the Mariner Valley, and it's more than 4,000 kilometers long. It's 200 kilometers wide. It's 7 kilometers deep. This makes the Grand Canyon look like a scratch, right? This is a true rift valley. How did it form? We don't know, but it definitely was formed with some kind of, liquids and things like that. We don't know how, but we know that it had to happen pretty quickly. I mean, there's little clues. Don't worry too much about that. You just have to know about this giant scar across Mars. It's like the size of the United States. Okay, it would fit, but not much extra room. Okay, so Mars does have ice caps, and one of the neat things that we can see is that they are seasonal. Okay, the thing that you probably didn't realize is that the ice on Mars is made of the same stuff that the atmosphere is made of. And the atmosphere on Mars is about 100% CO2. So the ice caps that we can see are made of CO2. Now, this is important. Underneath the ice caps, there's more ice, right? We've discovered that there's more ice underneath the surface of Mars than we had any idea of before. So recent developments have shown us that there's ice under Mars' surface, lots of it. And these ice caps are particularly prone to form at the poles, where we have lots of ice, miles, tens and 20s of miles thick ice. So let's see, we mentioned the seasons. We would expect on just guess that the Martian seasons would be about 1/4. And they're pretty close, not exactly, because Mars has a slightly more elliptical orbit. So don't worry too much about that. But anyways, there is water on Mars. And we definitely know that underneath the poles, there's lots of ice. And I'm about to tell you one of the coolest facts about Mars in just a moment, okay? You're supposed to know a couple of things about the atmosphere. I did mention that it's just about all CO2, 100% CO2, but very thin. The pressure at the surface of Mars is only 1% the atmospheric pressure on Earth. You should know that. Please write that down, right? The atmospheric pressure on Mars is 1% that of Earth. So you could imagine, right, that one day maybe humans will be walking on the surface of Mars. Could they walk without a spacesuit? And the answer is nope, you cannot. It's like going into the upper atmosphere, stratosphere, or into space. The moment that a human body would be out exposed to such low pressure, your blood would just boil. Everything, any liquid material would begin to evaporate. So you have to use a spacesuit. So I'm not going to talk about it, but there are people who are talking about how to change the Martian atmosphere to give it more pressure. And if you could, it turns out if you could get to 40% of the Earth atmosphere, then all you would need is a scuba type of apparatus to breathe with, and you would be able to run around on the surface of Mars with just that. Okay, so that's a potential for the future if humanity develops this technology. We do see wind on Mars. If you saw the movie The Martian, the only thing I hated was the whole premise of the movie, which is that this giant windstorm comes up and blows and causes an accident. So that could never happen, it turns out. The wind, even though it blows, can never actually pick things up because the density is too small. But there are little dust devils, and we've actually seen evidence of little dust devils on the surface of Mars. There are clouds. There are some made of water and some made of CO2, and fog, and things that we might expect to see on Earth as well. So there's something familiar too about the weather patterns that we see on Mars. Okay, so here are the two moons, and the two moons are called Deimos and Phobos. And Deimos is the god of dread, and Phobos is the god of fear. So these, as you can see, are not spherical. So as soon as you see that, what do you want to say? Well, they're not big enough, right? They have small masses. They look, they look kind of smooth from these pictures. They're probably not quite that smooth, but they're pretty small. They do look very much like asteroids. Yes. So if they look like asteroids, they must be asteroids, right? Maybe Mars captured them. And actually, some of the people have said that, right? That's a great hypothesis. However, I want to make sure you know that our author, the author of our book, has actually worked with people to try to simulate and actually looked at the research trying to simulate this. How do you capture an asteroid and get it into a circular orbit? Because these moons have circular orbits. And the answer is no one has been able to show successfully a capture into a circular orbit. So we have a little problem. Even though they look like asteroids, they have circular orbits, which is not possible as far as our computer simulations are going. It's not possible to capture something like that and have it form. So they are both tidally locked. Remember what that means is one face is always facing towards Mars, which means they take the same amount of time to rotate as they do to make one revolution around Mars. And then I mentioned to you before, Phobos is actually going to crash into the surface of Mars. It's projected to be about 10 million years from now. So it is currently only 9,377 kilometers above the Martian surface. So it's going to crash, and maybe we'll get a giant Rift Valley after that. Who knows, right? So anyways, what do you need to know? You need to know that Mars, once upon a time, was very wet. So in the early days, we weren't sure, and this was like the biggest question. Did Mars have water? Blah, blah, blah. Is there any evidence? And when the rover, Curiosity rover, landed, and that in itself is amazing. I'm going to be posting a video you've got to watch. It's so exciting. Some of the cool videos of how they landed rovers, they are just phenomenal. And I'm so proud of NASA. It's such an amazing thing. But when they started roving around, one of the first things they found was blueberries. And you're saying blueberries? There's no blueberries on Mars, but they're not exactly fruit, right? What they're called, they look like blueberries, though, and they're actually little crystals of hematite. And these crystals can only form in a water environment, a liquid water environment. So what that means is that the water flowed over some other minerals and dissolved them, and then deposit and pooled in a little place, and then made these little spherical crystals of hematite. So we know that water flowed over the surface of Mars. We know that for sure. Another thing that we see is this. Oops, sorry about that. We see this picture doesn't show it very well, but we see sedimentary rock. So again, I don't have the best picture, but sedimentary rock is forming after year of deposition of grains of sand that eventually compress and form a rock. So Mars had a long period of being wet. And we think it was really in the earlier stages of its life. And I'll show you a little timeline in a few minutes, okay? But the very exciting thing that we have an orbiting spacecraft that's watching Mars all the time. And again, this could be a complete course on Mars, but it watches, and actually this seems to be a seasonal thing. There are these black streaks, and they're a little bit hard to, to say for sure. It could be like a landslide of some kind, but people think that it has something to do with salty water, very, very salty water that may be, melting from ice and then dripping down the slopes here. It may actually be underneath the surface, and then we only see this on the surface. We're not sure. Okay, nobody knows for sure what's going on. However, there's some news that you want to know, okay? In July 2018, the Mars Express orbiter detected subsurface water. Okay, there's a little lake underneath the surface of Mars. And this is it's underneath the ice actually. So there's an ice layer, but underneath that ice, we find liquid water. Okay, so this is pretty exciting. I told you earlier in this presentation that life requires liquid water, and we didn't know it when we sent the spacecraft to Mars, but there is liquid water, not on the surface, but underneath the surface today on Mars, right? One of the interesting things, there's a spacecraft that is also monitoring vibrations, Mars quakes, and actually has probed down, not very far yet, but into the surface to try to measure the temperature changes. It gets warmer as you go underground, right? So not only is there liquid water, but it gets warmer. It's not so cold underground, which means you have warm liquid water. Guess what? You have a place that could be hospitable for life. One of the really interesting things to me is we are discovering that life is everywhere on Earth, in the worst places that you and I could never survive, deep in the ocean, deep underground, and we find life everywhere. It just permeates our world, even underground, right? Deep underground, we find things that are alive. So this is a pretty exciting development. And so you want to know, July 2018, July 25th, we got the announcement that there is today liquid water under the surface of Mars. And in fact, they have estimated that Mars has kept perhaps 80% of its original water. It's not liquid, right? It's solid frozen water, and it's underneath the surface now, where it's kind of safer to be there. Okay, so let's talk a little bit about the history of Mars, and then we're going to name the periods when life was kind of a good time on Mars and when it wasn't so good, okay? So if you take a look right here, we have this period when Mars first formed, which is called the pre-Noachian period. Okay, now the core was molten, and if you got a molten metal core, what do you get? And you should say magnetic field. You had a dynamo effect. The surface temperature was pretty good, right? Surface temperature was good. You had lots of atmosphere, magnetic field. Habitability was low though, because it's way too hot still, right? And then something happened, right? As the crust formed and it cooled slightly, right? We got into this period, which is called the Noachian period. So if I ask you on a test, right, what time period of Martian history was the best for life? That's your answer. And it was between 4 and about 3.5 billion years ago. That was the best time on Mars. So we think that the surface temperature wasn't quite as hot. The crust had formed and was stable. It had a nice thick atmosphere, and of course, a magnetic field and liquid water at the surface. Okay, so the question is, what happened after that? So I actually, if we were in the lecture hall, I would title this lecture, "How do you destroy a planet?" Right? If you're an evil genius, right, or something, you want to destroy a planet, what do you do? How do you do it? Because it's happened. Mars was once this wonderful, wet world, which you and I could have potentially lived on. I don't know if we could have really lived on it without some help, but it would have been not so cold. It would have had magnetic field with shields. It would have had liquid water. It would have had all the things needed for life. And then what happened? Okay, so you want to know what happened. Mars is small, right? So what happened to the small body? It cooled quickly. And in particular, the core cooled quickly and became not molten anymore, but what happened? It solidified, right? So as the core solidified, what happens to your magnetic field? And so Here it is, right? Your core has been generating a magnetic field, but when it's solid, it can't do that anymore. The dynamo effect doesn't work. So without a molten core, the solid iron nickel core of Mars stopped producing a magnetic field. And so you might be like, well, no big deal, no magnetic field. Well, it's a big deal, right? The magnetic field around the Earth is protecting us from the solar wind. So without a magnetic field, you're not being protected from the solar wind. So what happens? Well, the solar wind, which is full of these energetic charged particles, comes into the atmosphere, energizes the atmosphere, and blows it away. So here we go. Lost your magnetic field. Now the solar wind can blow the atmosphere away from your planet. So what happens when the pressure goes down because you don't have atmosphere? What happens to the liquid water at the surface? It can't exist as liquid water anymore without the pressure keeping it as a liquid, and it evaporates into a gas. So when you lose your atmosphere, you lose liquid water at the surface. And then over time, right, when there's no greenhouse effect or a very small greenhouse effect, you're not going to be warm anymore. And finally, at the end of this period, right, we end up with our current period. So this period when the atmosphere was changing, when the magnetic field was changing, is called the Hesperian period. And it was about 3.5 to 3 billion years ago. And then since about 3 billion years, we think Mars has been kind of dead and not changing much, right? It still has a little bit of atmosphere, so it's not completely dead, right? We have erosion taking place. There's no plate tectonics to speak of. There's no volcanism to speak of, but it's still eroding what was there before. So that, in that sense, it is still alive, but just kind of weakly alive. All right, and that period that we're talking about right now is called the Amazonian period, and it has lasted from 3 billion years ago to today, okay? So Mars cooled off, the core cooled off and lost its magnetic field. Without the magnetic field, the solar wind blew the atmosphere away. Without atmosphere, the liquid water evaporated, and you are left with a cold, dry world. So this is basically what I was telling you before. The Noachian period was the best time, right? Mars had a magnetic field, molten core, active volcanoes, thicker atmosphere with water, liquid water at the surface, ponds, lakes, rivers. This would have been the best time for life to live. Now, what do you think would happen to the life and the material if Mars has been dead and you basically just have a little bit of erosion? Could there still be evidence of past life on Mars? And the answer is yes, it could be preserved, because Mars is like a giant time capsule. Things have not changed very much in the last 3 billion years. On Earth, nothing is the same, right? Things just the mountains have been worn away and new mountains have worn, on Earth, we don't have anything like this. On Mars, we have a time capsule from about 3 billion years ago. And so rocks that were made in that period, the Noachian period, might still exist. And we should be able to, if life was there, we should be able to see evidence of that one day. But it may take human beings on the ground that are more capable than the robots we have. It may be that. Okay. All right, so I went through all of this. You should know the stages. Okay, this is way too much information. Let's try to highlight what's important. And you could look at the slide set to maybe look at it a little more carefully. The size is important, okay? The size of Mercury, you're supposed to remember, is a little bit less than half the size of the Earth. Size of Venus is almost the same. It's 90-some% of the size of the Earth. And then Mars is a little more than half the size of the Earth. The mass, don't worry too much about. The densities are going to be pretty similar, although what do you notice about Mercury? Its density is higher than the rest, right? Why would that be? And the answer is because it has more metal and less silicates. Take a look over here at Mars having slightly less density. Can you give me an answer why it might be less dense on average? And so this is the Earth density, and Venus, they're almost the same. But Mars has more silicates. So metals are more dense, silicates are less dense. The average density is between them, okay? Mercury has no atmosphere. Venus has carbon dioxide. Earth is nitrogen and oxygen, and Mars is just carbon dioxide as well. The atmosphere I mentioned to you already is about 90 times Earth atmosphere. I'm going to disagree with this. I'm going to tell you it's closer to 1%. 150 I don't think is quite right. Surface temperature is kind of cool. Surface temperature of Venus, 730 Kelvin. Earth is about 300. And Mars, if you take a look, is quite a bit cooler, right? Because it doesn't have enough of a greenhouse effect to keep it warm. Does it have caps, ice caps? Mercury, no. Venus, no. But Earth, definitely made of water ice. And on Mars, there's carbon dioxide on the top, but water ice underneath, okay? And radius, not so much. How about the orbital period, though? Let's you should know that, right? For Mercury's about 88 days. Venus is 224 days. Oh, I said 256, it's 243. I made a mistake. And yeah, so the year, that's kind of, you see it's getting steadily longer the further you get from the sun. And the rotation period, you can see 59 days for Mercury, one rotation, 243 days for Venus, and then Mars is just slightly more than a day. And do we see anything else? No plate tectonics except for Earth. The age of the surface, very old for Mercury, right? Only, it says a billion. I think it might even be million, by the way. I think it's changed. And then Mars maybe is potentially 3 billion years old. Yeah, so, and then the last thing, I guess, to the moons. Yeah, you should know that. There's no moons on Mercury, no moons on Venus, 1 for Earth and 2 for Phobos and Deimos. And I think that is the end of our slide set. Those are the terrestrial planets, and we studied tonight. One more thing, sorry. One more thing, and I think I didn't really mention this too much, and I gave you a quiz question, so hopefully you watch this before you take the Chapter 6 test. But the question has to do with Earth and our atmosphere. It's made of nitrogen and oxygen. But what was it originally? And the answer is, well, we think that the primary or first atmosphere for every planet is going to be carbon dioxide, every planet. So Earth would have had carbon dioxide as well. And actually, I'm going to go ahead and talk to you guys in person. So everybody gets carbon dioxide to start with. Where does the carbon dioxide come from? Well, it turns out volcanoes emit carbon dioxide as part of their process, right? So we think that because everybody has volcanism, everybody has carbon dioxide. So Venus kind of stuck with the carbon dioxide, and Earth did not, and Mars did. Okay, so but what happened with Earth? Something different. We ended up changing and losing most of our carbon dioxide and leaving behind what was originally just traces of gases, nitrogen and oxygen. How did that happen? And the answer is life. Life on Earth did something amazing. It incorporated the carbon dioxide into the body of the organism, right? So life took that carbon dioxide in and then lived and then died. And most of the life would have been in the oceans, and it would settle down to the bottom of the ocean. And year after year, these layers form and eventually form rock, right? So when I ask the question, where is the carbon dioxide that used to be our atmosphere on Earth? The answer is it's stuck in the rocks of Earth. It's still here, but it's locked into the rocks. You can find it. There's a chemical compound called carbonate, and you can hear it has that carbon. It's actually got even a little more oxygen, but it's got the carbon dioxide would have been incorporated inside of the organisms. So the difference between Earth and the other planets is we know that life had a really solid foothold and was so abundant that it changed the atmosphere of the Earth. And that's a big thing. Now that didn't happen on Mars and Venus, apparently. Or if it did, it happened way before the time that we're looking. And we have no evidence now to see that. All right, so that's it for our terrestrial planets. Thank you for joining me. And don't forget to take your quiz, read the chapter, look at all the extra things. I think that they're probably the best part. I would be showing you those in the lecture, because I don't want to show you during this lecture. I'm just making the lecture and then adding them on. But please do watch them because I think they kind of enhances what you're learning. So thank you so much, and have